Welcome. My name is Craig Messmer. I'm going to present small ducts for small loads, the use of small duct high velocity systems in low load homes as the best system for these types of applications. The way I've structured this presentation is to first give you a definition of what a low load home is. You may or may not be familiar with that, and give you a definition of what a small duct high velocity system is. There's an official definition for SDHV. Then we're going to discuss what makes a low load home unique in terms of sizing and selection, how it's different than a typical residential application, and why small duct systems are perfect for this application. Finally, we'll follow it up with a few real world examples where SDHV is used in low load homes. To begin with, what is a low load home? Well, there isn't any official definition. The closest that there is was made by ACA. ACA developed a publication on low load homes that they published about 1 year ago. They call it the manual LLH, and it's a very good design guideline. If you're going to be doing any design work for low load homes, I encourage you to get a copy and review the guidelines that they provide on what type of system is required and how to calculate the loads. They came up with some proxies for what a low load home is. Basically, it's significantly less load than a normal, what today is considered a normal house. Okay, our typical house today is 500 square foot per ton. That is improving because of building codes and better insulation. And a very high performance home is in the neighborhood of 800 to 1,000 square foot per ton in cooling. And a low load home can be as much as 1,500 square feet per ton. Now, in heating, it's similar situation. You're looking at 800 square feet per ton for heating, and that's typically with a heat pump in these low load homes. Although there are some low capacity gas furnaces available too, but not very many. So you're looking at really about a third of what you normally get, very low loads. Where do you find these? Well, you find them in multi-family applications where they have one exposed wall and the rest of the apartment is surrounded by other apartments. So it's a very low load application. Also in mild weather climates, Hawaii comes to mind. These are few and far between. Most people don't live in those buildings or locations. So where you are, you might have a super insulated home. This is probably the more commonly thought of low load home application. These are super insulated and very tight homes, much smaller loads than even a high performance home. A small duct high velocity system has an official definition. It was created by the Department of Energy about 15 years ago, although these products have been on the market for probably 40 or 50 years. And it's very specific, a maximum of 350 CFM per rated ton. In practice, the number is really about 300 CFM per rated ton. There's a range depending on manufacturer, make, model, and so on and so forth. That will vary between 280 and maybe 320. Also, you have to have at least 1.15 inches of static pressure external to the unit. That's a higher pressure than a normal furnace blower. The registers are quite small, less than 6 square inches typically, and delivering the high velocity, 1,000 to 2,000 feet per minute. Looking at how this compares to a more traditional conventional ducted system, and even a ductless mini/multi-split unit, you can see that the airflow rate is significantly less than what you normally find. Conventional is usually 400 to 450, and the ductless mini splits are typically somewhere in between what a small duct system would be and what a big duct system would be. Minimum external static pressure, that's changing somewhat for the conventional systems. Right now, it's a range between zero point 0.1 and zero point 0.3 inches of static pressure, depending on capacity between 1 and 5 tons. The same with the small duct high velocity. It's also a range which is 1 inch greater, 1.1 to 1.3. Starting in 2023, the Department of Energy, in an effort to mirror what you typically see in the real world, how they're installed, has raised the conventional external static to zero point 0.5, and it's without any range. It's 0.5 for all capacities, and they fixed it for the small duct systems at 1.15. Usually, the small duct systems operate pretty much the same static pressures that the products are tested at, and conventional will be starting in 2023. Ductless mini splits obviously don't have any ductwork, so that doesn't really apply. The register sizes are significantly smaller, 2 inches in diameter typically for a small duct system, sometimes 2.5. There are a few that are 3 inch, although it is a little bit bigger than 6 square inches, which is typical. Conventional systems are registers. We've all seen them, probably have them in our own homes, 4 by 10 inches, sometimes 4 by 12, 4 by 8, in that range. Ductless mini splits don't have registers or grills per se. It's at least not separately, not ducted ones. So the unit itself is the register or grill, so they're quite large. Velocities are, of course, much higher for a small duct system. You're looking at the discharge velocity coming into the room at 1,000 to 2,000 feet per minute, commonly around 1,500. That's probably the average that I've seen. Conventional big ducted systems are usually 2 to 400, usually around 300, maybe 400 feet per minute. And ductless mini splits are a little bit higher when you have them turned on high, which is where you usually rate them for maximum capacity. And not really a small duct velocities, but a little higher than normal register. So that's how they compare. So what's a good system for a low load home? What's different? What do you really have to pay attention to? Well, let's start with the loads. Okay, they are much smaller. They're extremely small. So that means you have smaller sized equipment, and smaller sized equipment means you have a lot less airflow. So therefore, effective air distribution is very, very important. When you have a super insulated home, there's a few other requirements. One is you're going to need fresh air ventilation, and the sensible loads, of course, are going to be decreased. But interestingly, the latent capacity does not change all that much. It's typically from the internal loads, which are breathing, showering, cooking, and the moisture really has no place to go because the homes are that tight. So the sensible heat ratio is going to be closer to 0.6, zero point 0.5, and normally right now you typically have around 0.8. So significantly larger latent capacity relative to the sensible. Low load homes, because of this moisture buildup, in the more mild times of the year, you could have dehumidification without cooling. That's a little different. Most houses today don't really worry about that. They have enough infiltration, and the systems are running long enough, even in those off peak months. And they lend themselves to zoning because if you don't have enough air moving throughout the house, it makes sense that you have separate systems to heat or cool the different areas of the house. We talked about the loads being very important. Well, that's actually the problem with a low load home is that the loads are so low that contractors, designers don't believe that they're that low. The heating and the sensible cooling loads are likely to be very similar, even in a cold climate zone. To put it in perspective, the water heater could have more of a heating load than the space heating condition, than the space loads. And we talked about the latent loads being close to the same and sensible loads being much smaller. So your sensible heating ratios are going to be around 50%. That's quite low. Air distribution is probably the most important criteria for a good HVAC system in a low load home. NREL did quite a few studies on low-load homes in different types of systems, and they've concluded that air delivery is key. So how do we do this? Okay, there are three basic ways to do it. You can spread the air out, which is normally done with grills, such as the one shown in this picture. You can mix the air with fans, or you can have induction airflow, which draws the air into its airstream and mixes it up. So when you spread the air out, you do that through the grill, which we saw previously, and it has louvers. And the angle of the louvers is important, and so is the velocity, because you want to have as wide of a coverage as you possibly can, given the size of the room. And then you want to have your return opposite of the supply, so that the occupants are basically in the airstream in a low velocity, gentle blowing airstream. This is very hard to do, and it's hard to find places to put the supplies and the returns, and it's hard to get the velocities right and the spread just right. So often you're left with stratification, drafty, and you can have some dead zones where there's just really not enough air uh, in that particular area. So it can become quite stuffy. So these are problematic and difficult to design too. And if you have a system that has low air volumes to begin with, it makes it even more difficult. You can mix the air up with a ceiling fan. That actually adds energy into the space. So maybe not always the most efficient way to do it, but it does add to the comfort of the space, and it's a good way to do it. And maybe it's something you want to do when you're not actively heating or cooling. So ceiling fans have their uses. Probably the best system, though, is to use induction flow. And both ACA and NREL in their studies came to this conclusion, where you have a high velocity jet of air that you blow into the room, and it will kind of pull the room air into it and create a gentle mixing action surrounding the jet stream, so that the nozzles don't point at the occupants but away from the occupants, so the occupants are in the secondary airflow. We demonstrated it using flash photography in a lab, University of Illinois, Peoria. These are neutral buoyancy air bubbles, and with the flash photography, we could determine the velocity streams, and we're able to define the jet cone, if you will. And in this case, the configuration was a 2-inch nozzle, and it had about an 8 foot distance to the other wall, and you can see the gentle mixing air outside of the airstream. As long as you put the nozzles in the corners, you're not going to have any drafts. Oak Ridge National Labs did a test in one of their test labs where they measured small duct high velocity system and a conventional system in the same house every other week, and measured the air velocities, temperatures, humidities from head to toe in various rooms of the house. And if you overlaid the two charts from the study, you can see that the small duct systems always have less stratification than normal grills. So it does work, it's very effective, and it adds to the comfort of the occupants. Latent loads are very important as described, okay? They also add to the comfort. Okay, you can improve the latent capacity by using less airflow, 300 CFM versus 400 CFM per ton. This means that your supply air temperatures are lower, and so is your equipment's sensible heat ratio. By doing so, you get about a 25% better moisture removal at steady state conditions, at rated conditions. Florida Solar Energy confirmed this in some of their studies, where they measured the supply air temperature and the room relative humidity, and they found a direct correlation to this. So at air temperatures around 60 degrees, which is common for a big duct system, at 400 CFM per ton, you're going to have, or they measured close to 60% relative humidity in the space. It's a little high. Most occupants would tend to turn the thermostat down a few degrees, kind of keep the moisture down. And of course, there's an energy penalty when you do that. Whereas a small duct system, which had lower supply air temperature, would maintain the same room at closer to 50% relative humidity. The occupants wouldn't have to change the thermostats, and any dehumidifiers that would be needed didn't run or ran for very short periods of time. Very important in a low load home to keep the air mixing. Otherwise, it becomes very stuffy in the house. And I've experienced this myself in touring one of the homes in Pittsburgh. When the system was turned off, it really felt like you couldn't breathe very well. So you kind of need that air movement. It's very important for human comfort and probably the reason why we have heating and cooling. Well, small duct high velocity has other benefits besides those two. Obviously, comfort is a big one, and this is done by having good mixing, better dehumidification, which we've talked about. Also, warmer air if you're heating with a heat pump. It has to be quiet. It's part of being comfortable. It has to look good. Nothing is less unobtrusive than a 2-inch hole in the ceiling, and of course, it has to be efficient, and they are. By efficient, they have to you improve efficiency by keeping the ducts inside the conditioned space. Small ducts make that more possible, and if you don't, you have to put them in an unconditioned area. Then you better make sure that they're well insulated and then they're tight, which small duct systems are. And of course, the surface areas are much smaller, so all in all, it's a good thing. And better dehumidification improves the efficiency and the way you operate the equipment. They have to be economical, and that means they're easy to install, easy to design, and the small duct systems meet that criteria. In terms of noise, we've measured the sound pressure levels from the registers. All the small duct high velocity manufacturers uh, have a sound attenuator, which is like a muffler, and does a very good job of keeping the noise levels down to a minimum. These are very quiet systems. I've seen them even installed in sound recording studios. So uh, that's not an issue, although some people might think it is because they hear the words high velocity and think noise, and that's just not true. So kind of following up, the small duct high velocity has low thermal losses. It's great for efficiency, high R factors. The insulation is a little bit more dense than a normal flex duct, and the very tight connections usually gasketed. Okay, check, check, check. Relative humidity, don't need a dehumidifier at all or very often. Okay, no drafts, warm discharge for heating. Very, very nice. In the study from Florida Solar, they were able to show, because of these nice features, that on a monthly energy use basis, the same house using a 14 SEER small duct system compared to a 22 SEER conventional ducted system, the total energy use was less for the small duct system. It was interesting because often people look at the different efficiencies, and small duct has their own product classification, a lower minimum efficiency, and you would think that it would be less performing. It's just not true. In terms of economical installed cost, uh, in one of the reports from NREL, they polled some contractors to give them quotes for installing a small duct system and a big duct system in the same house, and they were similar in terms of what equipment was in there. And the bottom line is because they didn't have to do as much construction, and the installation was easier and more straightforward. They had less labor. The small duct system came out a little less. But the point is that small duct systems are not always less efficient, and they're not always uh, more costly. In fact, if done right, just the opposite will be true. Builders are using them now. Uh, they are used in low load homes. The one on the left is a home in Pittsburgh. The one on the right is a multifamily unit in Denver, Colorado. And here's a couple of other homes, that one in Charleston and Huntington Station. These are both award-winning net zero homes by the builder. So they are used quite often. Rounding it all out, small duct systems are just made for low load homes. Okay, effective air distribution, enhanced dehumidification, fits inside the conditioned envelope, provides comfort, efficient, economical. I'm not sure what else you can ask in an HVAC system. And if you do it right, you'll have a lot of happy customers, I guess. So uh, here are some of the references that I used in this presentation. I'll leave it up for a minute here, a moment, and you can come back to refer to it if you want to search out more information on your own. Whoever has the first question, fire away. Thank you very much.